Hey guys, what's going on? It's me, Mr. V. Today we're going to be learning about periodic trends and just think about the term trend and how a trend is just, what's trendy, what's the repeating patterns that occur. Obviously like style, there's trends that you see. So what happens every so often? What repeats? So this whole unit periodicity is about how whenever you arrange elements in order of atomic number, you start seeing patterns. Just like that activity you all did last week, where you created your own periodic table, you saw that there were patterns and groupings that repeated regularly. Well, that's what periodicity is all about. So we're going to look at certain properties today, and we're going to see how those properties change or are affected as you go across and down a periodic table. The first property is atomic radius. So, what is the radius? What does that mean? You have to answer. A what? So, what can we find the radius of? A circle, right? So, what is the radius of a circle? Well, what's the diameter? Okay, so the diameter is the full way across, so the radius is halfway across. So, just like in math and geometry, the radius is a measure of the size of a circle, essentially. You're going to see the same thing here. As of now, we've been showing atoms as circles, as particles represented usually as circles. So whenever we talk about atomic radius, we're just talking about the size of the atom, but the textbook will define it as half the distance. Just like in a circle, the radius is half the distance, not like the diameter, which is the entire distance. But this is not from the center of the circle to the outside of the circle. It's half the distance between the nuclei of two identically bonded atoms. Now, we'll break down what this textbook definition means, but simply put, what we mean when you hear the term atomic radius is the size of a circle. The size of an atom, specifically. So on the right, you see the radius of a circle. It shows how big that circle is. It's a measure. We can compare sizes of circles to each other by comparing the radius, or the radii of those circles. Well, we don't know where the outer boundaries of an atom actually are. We don't know where that last ring or that outer circle is. So they look at two identical atoms. So let's say these are two oxygen atoms bonded together, and you measure the entire bond length. If you cut that in half, it's essentially like cutting the diameter in half and getting one radius of one of those circles of one of these atoms. So that's how it's measured, and that's how it's established to simply mean how big that atom is. Now, if you look at the periodic table, these are the trends you're going to see. Now, we know why why it gets bigger when it's going down. At least you should after looking at that activity last week. Everything in row 1 has how many rings? One ring. Everything in row 2 had how many rings? Two rings. So here's one, and then there's that outer one. Everything in row 3 had three rings. So of course, what's going to happen as you go down a family is you're going to increase the energy level. So on the right, why is it larger going down a group or a family? Well, you're increasing in energy levels, which means you're adding more rings. And more rings makes the atom larger. So paraphrase this however you'd like, but simply put, the lower you go down the table, the more energy you have, the more rings that are occupied by the more electrons. So if this is period 2, we see the first ring holds 2 electrons, and it has a second ring holding some electrons as well. Whereas a period 3 atom would have 3 rings. So while on the left you see ring 1 and ring 2, on the right you see ring 1, ring 2, and ring 3. So every time you go down a group, you go down or up an energy level, up in the number of rings. Naturally, it's going to make the atom larger. But let's look at this picture again. It makes sense. As you go down, you're adding rings, the atom's going to get bigger. But what's happening as you go from left to right? They're getting smaller. And this one's a little harder to understand. Why is that happening? So what ends up happening is the number of rings does not change, right? Everything in row 2 has 2 rings. So you're not actually losing rings or making the atom smaller. It has the same number of energy levels, but you are increasing the atomic number every time you go from left to right. The atomic number goes up by 1, which means the number of protons goes up by 1. Now this picture is just showing an illustration. The idea that if the ratio increases, well, the ratio doesn't change, but the number of protons increases, then the number of electrons will increase also. So here in red, this is really what you need to focus on. When you go from left to right, look what's happening to the nucleus. Here, the nucleus is +1. Here, it's +2. As you go on, it's +3. And then finally, +4. And again, this is just an illustration. This is not actually a true row in the periodic table. But you add to the power of the positives. So think of it like a magnet. If you had a positive end of a magnet and its power was 1, that's probably weak compared to a magnet that had the power of 4. Well, the same is true for the negative part of this magnet. Here you have -1 on the outside, -2 on the outside, -3, and -4. So this +4 power on the inside and this -4 energy on the outside, those are going to have a stronger attraction. The positive is stronger, the negative is stronger, so the attraction is going to become greater. And so the electrons move in closer because they're more strongly attracted to these positive protons. So basically think of it as these electrons kind of cuddle in closer to the nucleus because the attraction to the nucleus is stronger. So as you go down the periodic table, they get bigger, but as you go to the right, they get smaller. So on your periodic table, draw the trend lines. For atomic radius, you want to draw an arrow pointing down, explaining how these atoms get bigger as you go down a group. But they get bigger from right to left because of the attraction that the protons have for the electrons. On the right, they're cuddled in very close together, and on the left, they're kind of more spread apart. The attraction is not as great. So across the table for atomic radius, you want to draw an arrow to the left and down. So overall, this is what the trend looks like. It starts here, and it goes to this corner. So this corner up here would be your tiniest atom, and this corner down here would be your largest atom. This is the largest because it has the most rings, and because the electrons aren't as attracted or cuddled in as closely. So one thing you're going to be asked a lot is which atom is bigger or which atom is smaller. And as long as you could follow this trend line, smallest up here, and then down here in the lower left, you have the largest atom, then you could remember how these atoms relate to each other in size. And there it is. So if nitrogen approximately had a diameter, radius, atomic radius of 0.75, and arsenic had a radius of 1.33, what do we know about phosphorus and its radius? How does it compare to these two? Well, it's going to be somewhere in the middle, right? It's going to be greater than 0.75, but less than 1.33, because what we know happens is it gets larger as you go down. So what would be a reasonable answer for the size of phosphorus? I don't know, maybe like 1 point something. Less than 1.3. 1.05, anything between these two values, as long as it follows the trend, it makes sense. All right, the next property is electronegativity. You see a few words in here. The first word you see is electron. The next word you see is negative. So what do we know about the electron and its charge? Well, the electron is negative, so this property is all about the electron. It's the measure of the ability of an atom to attract electrons. So what does that mean? Simply put, it's the atom's desire for electrons. Just like people, some people can attract more people to them. Maybe they're friendlier, they're more outgoing, I don't know, better looking, anything. That might attract more people to them. They would have a stronger attraction to these electrons, these atoms. So it's a measure of how attracted these electrons are to these atoms, or how much these atoms desire these additional electrons. Now, what we've seen in the periodic table is everything in group 1, your alkali metals. They have one valence electron. That means one electron on the outer ring. If you recall, how many electrons do all atoms want in their outer ring to fill it up? How many will fill up that ring? 8. So they all want 8. But group 1 doesn't want to gain 7. It wants to give away this one electron. And by giving it away, it has a filled shell just below that outer shell. So group 1 elements have no desire for electrons. In fact, they want to give them away. But a group 17 atom, the halogens, have 7 valence electron. They need 8, like all atoms want. They need 1 right here. So while group 1 wants to give it away, group 7 wants to take it. So group 1 has no desire for electrons. Group 7, they have a very strong desire for electrons. They really want that electron. That way they could fill up their outer shell. And then group 18, the noble gases, do they need any more electrons if they already have 8 in their outer ring? No, they're done. They're filled. So they have no desire for electrons at all. That's why the noble gases, they're kind of the stuck-up ones, kind of off on their own. They don't need anything from anyone. So that's what you're going to see here. When it comes to electronegativity, let's draw the trend lines. The noble gases, you want to circle them and indicate they have 0 desire for electrons. Now what you're going to see on most periodic tables is that's not true. There are some electronegativity values for some of the noble gases, but for the sake of what we're explaining here and in this class, and really for what you need to understand in chemistry, let's just say that they don't want electrons at all. They already have all 8 that they need. Now group 17 really wants electrons the most, so this desire is very high, and group 1 has a very low desire for electrons. As you go down, they have even a lower desire for electrons. As you get farther out in the rings, they kind of don't care about what's happening so far out in those energy levels. So the highest electronegativity value is here, so it starts down here and gets higher up to this point there. And you can see that overall trend illustrated by that arrow. Now here you can see actual values of electronegativities, and you can see fluorine is the most electronegative with a electronegativity value of 4.0, so that's the highest you'll see. Basically, again, it's how badly do they want electrons. Fluorine really wants an electron. Fluorine's desperate. Francium, on the other end, way down here on